the second lecture on physical layer security. I have to confess, I turned it completely upside down. So you will find the slides online, but several people told me they would like to hear a little bit more also about the companies I'm involved with and how to go, from theory to practice and to products and into the market. So I will still talk about the technical stuff, but I added here and there a little bit of spice regarding entrepreneurial activities and the things that you can actually do with information theory that go beyond proving theorems and writing papers. And so the second part is, I called it, just practical physical layer security. It's part of a keynote I gave at ICC last year. Feel free to interrupt at any point in time. If you have all sorts of questions, they don't have to be technical. They can also be, about life, death, the world, and all of that. I have no answers, but I love to talk. So here we go. So if there's one thing that really, really changed, and to convince you why it's important to look at the physical layer and to look at security at the physical layer, and it continues to be very important, is that mobile is taking on the world. In 2005, that's when Cardinal Ratzinger, or Pope Benedict, became Pope. This was the picture that they took. In 2013, they took the same picture, but when Pope Francis appeared. And this is how it looked, okay? And so you can see the difference, right, between this picture and this picture. This is how fast technological change takes over the world, okay? And so when you look at the numbers, there's no doubt, okay, that this change happened precisely, in those 7, 8 years. You start seeing that eventually mobiles, so smartphones and tablets, outperformed PCs in terms of sales, and it kept growing. So there was an inversion point in 2011. And today, we are way ahead in terms of mobile devices that are connected to the internet compared to laptops and PCs and fixed computers. And much of the developing world actually is coming onto the internet through mobile devices and not through computers instead of computers. So this is a huge change and definitely a trend that forces us to continue to think about wireless signals and the physical layer. The other one is that we see a very strong convergence between initially, computation and communication. So that was basically the internet. You put computers and connect them to each other. You allow them to communicate. But now more and more you have aspects of control going into that, and even aspects of energy, if you think about smart grids and how all these devices with batteries and so on interact with each other. And so there's a very, very strong convergence where more and more machines are communicating with each other, controlling other machines and controlling processes and managing energy in various ways. Okay. And so the internet, which used to be a network basically of computers, laptops, and routers, and this is how for a long time we looked at the internet, is a very different jungle now with very, very different species, and for sure mobile devices, and each of these little phones has lots of sensors, cameras, microphones, accelerometers, compass, etc., and is actually more like a computing sensing platform than anybody else. It happens to make calls, but it does all sorts of other things. What is also coming onto the internet are vehicles, and so the connected vehicle is coming. And more and more, not only the car manufacturers, but also if you think trucks and buses and so on, want the vehicle to be connected. All sorts of embedded small devices with sensors, door openers, temperature thermostats, all sorts of devices are getting connected. Electrical appliances, and in fact nothing would please the utility company more than to be able to control all the devices in your home so that they can match load and production. And as more and more renewable energy gets into the mix, the more control they want to have on how power is actually used. And then anything where you can put an RFID or a little chip, today is connected and can be connected. And so, on top of that, many of these things are mobile. And if you think about wearables like this little fit device that is not doing a great job, is keeping me fit, but anyways, it tries. It walks with me and basically uses either my smartphone or my laptop to be able to send data to the cloud and tell me, how many hours I slept and how many steps I went and so on and so forth. And so it kind of works like a parasite in that, it has this little low-power Bluetooth connection, but it's basically then sending the data and using other more powerful devices to send the data back to the cloud. Okay? And again, wireless, mobile, and these are growing by the millions every day. And so when you look then on the industrial side, what enterprises and companies are doing, you have corporate networks that are controlling all sorts of workstations and basically actuating directly with the physical world. And this, from a security perspective, is an enormous challenge. Because whereas before the consequences of attacks on your system were basically loss of information and fraud and so on, today they may actually have practical consequences. For example, opening the gates of a water treatment plant can cause a huge flood, as it happened already in Australia through a cyber attack, or diverting a tram in public transit can result in very severe accidents that result in loss of life. And that also happened in Poland. And you're starting to see more and more examples of cyber attacks that actually have physical consequences. And so what happened, with the Sony movie about North Korea and all that was actually harmless compared to what cyber attacks can actually do on systems like this. And so we need to think about security, not just as an add-on, as we saw in the last lecture, where first we design the entire system and then we just add cryptography, but rather bottom up, we need to think very specific, especially for physical products and physical devices, how security is going to change it. And starting at the physical layer is really important, but then going all the way up to the cloud, where much of this is now being processed. Another example is smart grids. So there you actually go into people's homes, and so there's an important aspect there that we need to take into consideration. And then other systems. This is the harbor in Porto, where we actually build a wireless network that is able to connect all these moving machines, so not just the trucks that carry containers, but actually the patrol boats, the cranes, all of those need to be connected wirelessly, which is a huge challenge because they have all these metal walls here, and so signal propagation is really bad. And this is an area where they're completely frantic about security. Because imagine one of these little things falls on, on someone's head, and every second counts. So the need for real-time information that coordinates this and avoids accident and allow them to be very, very efficient is really important. So here's a small movie of this vehicular mesh network that we built. It's a day in the life of vehicular mesh network in Portugal. And so it's 7 a.m. And these are the access points, and the little dots are trucks and boats and other moving machines. So they start working, and green are vehicle-to-vehicle connections, and blue are vehicle-to-infrastructure connections. And so say during the day, they go about, and you see how the mesh network is helping them overcome the dead zones that happen between the containers. So now they're having lunch. And then at 1 p.m., it just goes back to the whole. So this is not simulations. This is not mathematical model. This is a real wireless signals and measurements, and the intensity gives you the quality of the signals and how you use it. Okay. And so to design the security for this system, we actually started right from the beginning thinking how to protect not just the data that we are transmitting, but also the devices themselves and these links, and making them as secure as possible. Now it's dinner time, and then they go back to work. So it's a 24/7. Right now it's a 24/7. At the time, they stopped between midnight and 8, so they should be stopping more or less around now. All right. Then the second thing is, how do you go, from a network that is in a controlled space, contained, where you actually have control over everything, to a network like this that actually covers the entire city. And that's what our company Venium does, is we build networks of connected vehicles, not just for the controlled spaces, but actually also for the entire city. And now the security becomes even much more complex in that this vehicle is connecting not just to cellular, but also to the existing infrastructure, like Wi-Fi. It's connecting to other vehicles, and it's connecting to all sorts of devices of people inside of the vehicle, but also outside of the vehicle, and all sorts of things that are gathering data and using the vehicles as data couriers to send that data, just like my Fitbit device does with my smartphone or my computer. And this is downtown Porto, and this network already exists. So we have a commercial deployment with more than 600 vehicles, which includes the entire public bus fleet. So it's offering free Wi-Fi to 90,000 people. It's also gathering terabytes of data that the city is now using to be able to manage their operations and make the city a more pleasant and efficient place. And actually, I was not going to show you the video, but I can't resist it. I'll just show it to you. So it's just a few minutes, and then we'll go back to algorithms and theories of automation. All right, so this is the video. And I don't know if the sound is going to work, but I'll stay here and probably my microphone is able to pick it up. All right, so let's put this on full screen. Let's see.
Internet connectivity is a fundamental pillar of today's society. To be connected in today's world means that no matter where I am, I don't have to think about whether I'll be a black hole, whether I'm paying extra money, whether I'll have connectivity or not. I will just always know for sure that it's a seamless connection, whether I'm on a bus, on the street, in my office, in a city that I don't know. I'm always connected.
I think the network is more valuable when it is everywhere. Just like we expect electricity to be everywhere, we should expect network connection to be everywhere.
Venium recognizes that the internet is evolving to an immense ecosystem that connects millions of people and very soon, billions of things. Most of these things will be constantly moving.
Venium is building the networking fabric for the Internet of Moving Things. Our hardware, software, and cloud components allow vehicles and other moving things to connect to each other and share data with the Internet.
This is what we call ubiquitous information, ubiquitous communication. So everything will be connected to everything, will be communicating with everything. So this is our vision.
The vibrant city of Porto, Portugal fulfilled the key requirements for becoming the first deployment of Venium's technology, a living lab that proved the capability and scalability of Venium solutions. In the process, Porto became home to the largest vehicular network in the world, offering mobile hotspots to more than 50,000 end users.
Venium's network in Porto already has hundreds of vehicles, including taxis, garbage collection trucks, and the entire fleet of public buses. These vehicles not only serve as mobile Wi-Fi hotspots, but they also gather terabytes of data which they send from the physical world to the cloud.
Like the human nervous system, each device in this wireless structure provides valuable data, both in real time and delay-tolerant fashion. This huge amount of data can be monitored, collected, and analyzed, providing valuable insights on a city's status and condition.
Just a way to monitor the city with the use of technology, with the use of sensors, and so Venium provides the back-end infrastructure for that.
The smart city or the future city will be a city where the data will be very important in our decisions. So usually we talk about data-driven decision making. I think it's the only way that the cities will be providing the citizens services that are useful for them.
As global meeting points, container terminals and ports are very complex systems, swarming with moving things. Trucks, cranes, boats, containers, people. Venium solutions enable operators to deliver the cargo in and out of ships as fast as possible, in a safe and reliable way.
The speed of those connections, and particularly the low latency, the low delay, which is way smaller even than cellular connections, makes a big difference for their operations.
The Beyond delivering the hardware, software, and cloud components for networks of connected vehicles, Venium is building the networking platform that will ultimately enable the Internet of Moving Things.
After proving the concept in Europe, we set up our headquarters in Mountain View, California. This allows us to address the US and world markets and brings us one step closer to realizing the dream of a global Internet of Moving Things.
Venium, an Internet of Moving Things.
All right. So if someone asks you what is information theory good for, you can say you can build networks of vehicles that gather data and do all sorts of cool stuff. At least that's what I say. And going back to the problem at hand, so how do you secure a system like this, that has all these moving parts? Some of these devices have very hard constraints, and basically, are at city scale but completely distributed because it's impossible to control a network like this. It's not like the cellular network of a telecom operator where you can actually, have the fixed infrastructure, the towers, and everything in a controlled way. That type of architecture doesn't scale to be able to have billions of things and billions of moving things connected to each other. And at the same time, you want to get all this data to the cloud and then provide services to a system like this. And so traditionally, as you saw in previous courses for sure, you would protect the integrity of the message by using a hash function, then and sign it using private key of Alice in a public key cryptography scheme, and then basically use the same type of cryptography to share a key, and then typically use a symmetric algorithm to protect the data. And this is just a basic scheme. And on the other side, basically you recover the symmetric key using the private key of the receiver, of Bob in this case. You use that secret key to decrypt the message, and at the same time you verify the integrity by computing the hash, doing the check, and then this way you're able to guarantee that you have authentication, integrity, confidentiality. That's the simplest architecture, but it's not the one that has the lowest complexity. Okay? And the problem is that these algorithms, even with the elliptical curve cryptography, they're still pretty heavy. You have to have still, even with public key cryptography, some certification authorities that oversee the whole thing and certify that certain public keys are actually legitimate and can be used for that data. And so this is a very heavy architecture for the type of systems that we are considering. And again, none of this is applicable at the physical layer, except maybe a little bit of scrambling that you can do with stream ciphers. And indeed, GSM does a little bit of that at the physical layer. So the basic question is, the internet is changing so fast, so are standard cryptographic solutions good enough for these new species on the internet that we need to protect? And so the challenges that we find when we try to design this type of systems is that many of these devices have very low computational power. Even when they have some computational power, they also have to capture video or analyze all sorts of data streams, manage different connections, do also. So even when they do have some processing capability, it has to be divided among thousands of functions that need to be implemented at the same time. And so then battery constraints, so power efficient security protocols are necessary, so you don't want them to be constantly transmitting and constantly switching between receiving and transmitting and so on. Many of these devices now have GPS, so you can leverage context and offer location-based security. And for many of these things, you do have to do some application-specific design because the security criterions are not the same. And so you cannot have just simple, one architecture that solves all the problems. For some things, it's an overkill. For other things, it's not enough. And so in terms of engineering and security engineering, there's really a lot of thought that has to go into finding the right security solution for the system that you have and the problem that you are trying to solve. Okay. Now, how do we go from transactions papers to actually cover all the spaces that are actually building a successful business? And so I like to think in terms of a chain or innovation that goes from a theorem that provides a fundamental limit and trains your intuition to actually come up with an algorithm and then a protocol that basically is able to come as close as possible to what the fundamental limit to be. And of course, to be able to compute those fundamental limits, you have to do all these abstractions. And you have to imagine, for example, that your wireless channel is Gaussian with a certain fading coefficient, and then you go out and you measure, and wireless channels are everything but ergodic and with nice statistical properties. But the biggest value for me from information theory is not that it tells me that this is the limit, because most of my channels are not going to be exactly like the channel that we predicted, but rather they prove non-intuitive things. Okay, so what this means is that if I am an engineer, and engineers are very much driven by intuition, and I design a system, unless I educate my intuition, I will always come up with intuitive architectures that may actually be suboptimal. And so maths is a beautiful thing because it allows you to prove things that are actually non-intuitive. And this is why we need to continue to train our engineers in maths and to be rigorous and systematic and logical, but at the same time also to be able, so what fundamental research and basic research should be doing is surprise us. So surprise us with knowledge that was unexpected. So kind of maximum entropy research. Okay? And so then you can train your intuition and actually design systems that are so much better. And then you can actually go, from a theorem to an algorithm, then build a protocol, which is when you have multiple entities that need to communicate with each other, then system, build a system out of that. From the system then to actually have a prototype that is able to work with other systems and to integrate it is a huge step. And then to actually have a product that has all the features that your customers need and are willing to pay for so that you actually have a business, this is a huge step. And by the way, completely underestimated by most researchers and academics. So my experience, I didn't believe that like 5 years ago. But this part here, at the end of the day, is only, 5% of success in terms of getting your technologies and your solutions to be implemented in a very large scale overall and becoming a successful business. And so all these steps, and it's very rare to find people that can actually do everything. So this is why you need to build teams of people that know how to do each transition. But each transition is extremely costly in time, but also let me tell you, also in intellectual capability. Because again, we researchers and academics tend to think that all of the brains is here, and everything else, that's marketing and sales. Which incidentally, it's not true because for your system is rarely standalone. It has to work with legacy systems and other systems that exist. So you have to add layers and layers of interoperability, of functionality, that are not written in papers. Nobody to do that at the university, but without that, you don't have a product. And so that's extremely hard and requires a lot of intellectual ability. And this part requires an additional ability, which is the ability to listen. Because you only have a product if you have customers, right? And the only way to design the product is to understand the customers, and the only way to understand the customers is to listen to them. And sometimes even offer them something that they didn't expect, but you were able to hear between the lines, and they don't know themselves that they actually want it, but because you talked with them and you understand their problem, and you are providing with them something that they didn't expect. Okay? And so all of this requires intellectual ability, and in fact it requires a lot of strategies, it requires a lot of analytics in trying to understand also how an organization is built and how the different levels of decision making, and trying to figure out within all of this where are the needs of the consumers or the businesses, depending on what kind of market you're addressing, and you have to play a detective, and at the end of the day, the attitude to do that is not very different from the attitude in research. in that you formulate a number of hypotheses about where your product is going to be located, what functionalities it's going to be doing, what value it's creating to your customer, and then you design experiments, okay, that allow you to test that. For example, you go into one harbor and you start by deploying certain devices and nothing works, and then you fix them, and then you show it to the people who are operating the port, and they say that's useless to me, and then you say, so what would be useful to you? And oh, I would like to see, the speed and the fuel consumption of this vehicle and that hurts. And then you go, okay, so how do I do that? I have to connect my device to the onboard diagnostics unit. I get the data, I have to process it, then I have to wait for an opportunity to transmit, but he needs this within a certain time. How do I do that? And so then slowly, your product starts taking shape, and it's an enormous intellectual challenge. So the idea that the intellectual and the smartness and the gray cells are in the research fundamental piece is completely wrong, in my view. So in my experience, you need exactly the same kind of brain power at every stage of the innovation chain, and it's really, really hard. And part of the divide between industry and academia comes from a lack of understanding of each of the players in each one of these steps regarding the type of problems that need to be solved at each one of them. And so what you find then is that because this is kind of a layered process, you have specialists that specialize on proving theorems, others that specialize on developing algorithms, others that specialize on developing protocols, others that specialize on each one of these things, and then if you have business people that specialize on this. And they each one have their own vocabulary, their own models, their own filters and way, and very often people are just talking like this, and they have their own time scales, and they have all of that. So I think it's a huge challenge for society to actually be able to bridge the gap between all these different steps. And the sooner we start doing that, the faster we'll be able to solve the really big problems, like global warming, like food crisis, like water scarcity, like all traffic congestion, unlivable cities, and those are the really big problems that we need to tackle. And so as information theorists, I think that we can continue to have an enormous impact on the world, but I think we need to, or several of us, or many of us, have to do an effort to go from here to here, not by trying to do all of this ourselves, because I don't think that's possible, but by teaming up and doing the extra effort of getting out of your comfort zone and actually talking with people that understand the other pieces of the puzzle. Because what you will find is that the inputs that you get from those people are going to make you a better information theorist, because then you are going to formulate problems that are not only technically deep, but they are also practically relevant. And that's, I think, is the holy grail, is to be able to combine those things, and that was what Claude Shannon was able to do so brilliantly. Now, as I look in physical layer security at this, and particularly in information theoretic security, what I see is that you have tons of people right now proving theorems in this area, and I can see on Google Scholar, how the number of publications in this area continues to grow. I have to tell you, it's very surprising to me, because in 2005 it was like 3 research groups in the world that were looking at physical layer security, and it was very comfortable. We met each other, everybody knew each other, then it became 8, then 10, then 15, and I thought, it's going to be something that becomes popular, and then it fades away, and that's going to last like 3-4 years, and then something else will come up, and of course something else, polar codes and so on, came up, but then people combined some of those things also again with security problems, and so it has been steady and growing, and our book has been doing very well. So I'm surprised, but lots and lots of people doing here. Then what's surprising to me is very few people looking at coding algorithms actually for security problems. And I have to do a disclaimer here, which is I haven't been following the latest because startup just took over my life. But I was worried last year when I was looking at the papers. You continue to have people proving bounds for all. I mean, we now have the secrecy capacity of Nakagami fading and all those models. We have very few coding results, but I see that it's becoming more and more. But then you have even fewer people that are actually thinking of what it means to have security at the physical layer when you design protocols. So how do I do routing if I know that certain channels are more secure than others? How do I do accessing? How do I do congestion control when security is not an afterthought, but is actually right at the beginning a criterion by which I measure the performance of my system? Then there are even fewer people actually building systems that test physical layer security. And I'll talk a little bit about that later. So very, very few people actually build systems that are able to do secret key agreement at the physical layer or that are able to use secrecy codes. And likewise with prototypes, I actually only know one company that has a product, and it's not yet a successful business. So it's still at startup stage. Okay, so there is a lot of work. This is when you sell the company and you're okay. This is big. So the question now is, strategically, as you think of what do you want to do in this area, you're going to see that you'll have a lot of competition. It's very hard today, to have a theoretical result in physical layer security, information theoretical security, that is a breakthrough. It was much easier in 2005. Okay, so today it's hard, but it's 10 years. Oh my, it's scary to think that's already a decade. Oh my God. Okay, but there's so much work to do here. All right, and so when you try to think about your research agenda, find a space where you can actually make a difference. That has always been what I thought. For some reason, people like crowding, and Shannon also has a paper on that, like the bandwagon, right? Where people just like to jump on certain things, but the key to success in these other areas is to be able to team up with really great people that understand this very, very well. And then you can bring information theoretic ideas and influence how they design systems, which is what I found always most exciting to do. All right, so some examples of how to go from theorems to algorithms is basically to do code constructions that are able to achieve reliable communication and achieve a secrecy measure at the same time. Lately there have been more results on this, but as far as I know, we still don't have general code constructions that are able to achieve these two criterions provably, so that we're able to prove actually that they do. There was very early work by Andrew Tangaraj, which I always like to acknowledge because Andrew is the most humble, modest guy you can imagine, but his paper with Caldermang and McLaughlin very early on in doing LDBC code constructions for this problem. Several others then follow, but always for specific channels, like having a noiseless channel between Alice and Bob and a binary erasure channel between Alice and Eve, a noiseless channel again, and a binary symmetric channel here, and a degraded, so the Wiener type of channel. Then people started applying, so as I mentioned, polar codes and new constructions that were actually able to yield proofs of properties that combine reliability and secrecy, and also particularly for strong secrecy, as you see here, and Alex Vardy and his students have been doing some really good work there. But there's still a lot of work on how to build code constructions. With Cristiano, we also did some nice torus-based constructions for that. But again, you still have to go then from the theoretical constructs actually to implementing them and try. So what are the challenges? Is that of course random codes we know are not practical, so we cannot implement it in a system because we don't have enough processing and storage. Nested codes are practical, but the key challenge is that you actually don't know the channel a priori. You may know the channel, or likely you have channel state information about the channel between Alice and Bob, but you don't have Eve telling you, what the channel is, because the way we do channel estimation is that Bob estimates the channel and feeds it back to Alice, but Eve is unlikely to want to do that. So you have to do certain assumptions, like saying, okay, the attacker is not in this room. Do we have an attacker in this room? No? All right, there's one in the middle, so then there we go. But it is a safe assumption in certain environments that you say, okay, the attacker is outside with an antenna, a really powerful antenna, and try to, and so you can have some assumptions about that. Okay. The others is that the channels vary, right? They're not always the same. And so how do you do that with a coding scheme? So this is not different from the problem that you have in general with forward error correction. And so some of these codes have to have a noiseless main channel, which of course is hard. You make concatenate codes to do that and other things. But so from a practical point of view, this is there's still a lot of work to do. And so what our group said was that we're going to do, what best effort security. That we say, okay, we want to provide reliability, we want to provide some secrecy, and our goal is not to provide perfect secrecy, but rather to ensure that Eve has a noisy cryptogram, or as noisy cryptogram as we can make it, which is very different, because now I'm saying I am going to use cryptography and other means to protect the data. I'm going to use the physical layer to make it even more difficult for my opponent to be able to extract information from that cryptogram. Okay? And so then your code design also becomes different, because now you're not trying to achieve perfect secrecy or proving perfect secrecy, which is really hard, but you are trying to achieve high enough error probability at the opponent, at the adversary. And so one way that together with Willie Harrison and João Almeida and Steve McLaughlin that we did to achieve that was that we designed a code that basically creates a wiretap channel, and we use puncturing. And the basic idea is the following. If the channel is introducing errors, and I'm also introducing errors by puncturing, the adversary cannot distinguish between what are errors that I'm introducing by puncturing and what are errors that are introduced by the channel. Okay? And so this way I'm able to control, to some extent, how much information the eavesdropper is actually able to extract from the noisy cryptogram. So that's the basic intuition. This requires, of course, a shared secret, because I have to know the puncturing pattern, or at least the C that I use for a random number generator that tells me which positions I am going to puncture. And so this is a joint coding cryptography scheme that operates at the physical layer and has some guarantees in terms of the errors that you induce on the attacker. Okay. Another idea is, let's look at quantization. So how would I quantize things if I also had a secrecy constraint? And of course you could say, okay, I do the best quantization and I plug it with a code that basically gives me the best security performance, and then this concatenated solution gives me some point in the operation curve. Well, the first thing is, how do we define secrecy here? And one would be, I want to have a distortion between Alice and Bob, which is as low as possible, and I want a distortion between Alice and Eve as high as possible. Okay, and so it's again a different metric. It's not going to yield perfect secrecy, but it yields something that is practical and valuable, which is I can ensure that there is a certain level of distortion on the attacker's side. And so now we actually designed the quantizer together with the encoder, because this gives me a solution that has a lower complexity than having the optimum quantizer matched with the optimal secrecy code, which often I don't know what it is, right? So that's the thing. And so why do the quantizer? Because the quantizer, I know how to optimize quantizers for distortion, but this changes the problem a little bit, because now I have to minimize the distortion for Bob, but I have to maximize the distortion for Eve, and I have to do that both at the same time. And so this changes the quantization problem considerably.
I'm sorry.
Yes?
Are you concerned that you might induce noise or no?
So the question is whether Eve is allowed to induce noise. So Eve is a passive attacker. So I'm not looking, and actually in this lecture we do have some work on active attacks as well, but in this lecture I'm not covering that. No, I do have one slide with active attacks, because I'm covering a little bit of jamming further down the road. But that would be jamming, which can be either just noise, but it can also be structured jamming, where you actually send code word of structured signals. And so I will talk a little bit about those attacks as well. The other, in terms of how to design or how to think now about these codes, is just to say, I'm going to look at the properties of my code, and I'm going to try to use that structure and modify that structure in such a way that I'm actually able to achieve some degree of security, which again may not be measured in the optimal way by mutual information between cryptogram and message, and theoreticians are going to go, how can that be? Well, the thing is that if you keep the abstractions and if you say, I am not going to develop or implement codes that do not have provable security, then you stop system development. And so until theoreticians are able to come up with codes that we can use that have those provable properties, we just have to do the best we can with what we have. And that's basically an engineering approach to physical layer security. And that's the approach that we've been following. So here's an idea, is that typically you would have compression and cipher separately. And João Almeida and I worked on how to actually design compression algorithms that actually do the two things. So they compress them, but they also encrypt at the same time. So what was the motivation of this? So this one, I have to confess, actually was not motivated by anything practical. It's just, I just asked, so João was my master student at the time, and I just asked him, suppose that I have a Huffman code, and I want to make sure that that Huffman code is catastrophic. So we know that Huffman codes have error propagation as a practice, so a little error can cause lots of errors from down the road, but most of them eventually synchronize. And so I wanted to make sure that the channel always puts an error at the place where the code was going to synchronize, and this way, with an error pattern like that, it never synchronizes, and so you're never able to decode. I thought, okay, so this would ensure that if I'm able to place errors at the right spaces, then an attacker is not going to be able to decode my Huffman code because it never synchronizes. And so that was the basic idea. So I asked João. João was a computer science student who came up very brilliantly with a solution that generated, sequences that guaranteed for specific Huffman codes that they would never synchronize. But he also did that with the highest efficiency. So these sequences were also sequences that had maximum entropy, so they could also be compressed really easily. So we came up with this analysis by synthesis compression cipher, that basically what you do is that you analyze, you compress the data, you analyze and this analysis yields basically an error sequence. And so the encryption is basically by applying those errors to your binary compressed sequence, okay? And now I know that it's not going to synchronize. And so now I encode, and this becomes my password for that file. And it's basically the seed that generates that sequence, and that's what I share. And I can do that with a one-time pad because it's small. And now I share that with my legitimate receiver, so I share that with Bob. And what does Bob do? He basically, inverts the one-type pad, decompresses the arrow sequence, just adds the arrow sequence to the compressed sequence, and then I recover my sequence here. Okay? And it was just another way of thinking of how to design compression algorithms and systems. So we did this for Huffman codes and algebraic coding and all various ones. But basically, it's got us thinking that it's not specific for compression algorithms. You can do this also for channel codes. You can do this also for network coding. And for network coding, we came up with a way of basically when you generate network code. Did you have your network coding lecture already? Right? So you know that practical network coding algorithms, what they do is that they generate the linear combination and they put the coefficients in the header. So Luisa Lima and I basically said, okay, what happens if we only encrypt the coefficients and we leave the rest uncompressed? And under certain parameters on the code, you're actually able to have the mutual information between the payload of the packet and the coefficients is 0. So it's not possible to decode or to attack the payload by attacking the coefficients. And so you actually get away with only encrypting the coefficients and not having to encrypt the payload because it's already mixed. And so since when you look at how ciphers are built, the basic operations in Galois fields and so on that you use for, say, block codes are basically the same or very similar to the ones that you use for encryption algorithms like AES and so on. And so, since you have to do those operations anyways, one way to reduce the complexity is actually by doing coding and encryption jointly rather than doing separately. So there's another, field of places where there's tons of work and possibilities to do here. Okay. So as I mentioned, there's one company that actually has a product on this. It's called Whisper Communications. So whoever came up with that name needs a pat in the back. It wasn't me. Because Whisper Communications is just genius for a security company, right? So Whisper. And what they do, so this was a company co-founded by Steve McLaughlin from Georgia Tech. And they have an app that basically uses secrecy codes to protect certain transactions, okay? And they're using it now for a mobile wallet, and it's taking some time to be adopted because it requires you to educate your customer a lot of why this is better than anything else. But they licensed our patent and they are using it for this right now. Okay? All right, so in terms of the protocol, I believe that we should think about how to rethink the security architecture, so like kind of a bottom-up security, while you say, okay, I'm going to start by securing the physical link. And so the goal should be to have the physical link in a wireless system be as secure as an Ethernet cable. Okay, so that would be our goal. And then see what happens in each one of these protocols about that. Okay. Now, how do we do that in practice? So we need secrecy capacity achieving channel codes, and we know that's difficult. Okay. So in 2007 it seemed very difficult. I think that in 2014 it still seemed very difficult. But fortunately, secret key agreement, which is how to use the properties of the channel to actually generate secret keys, is an easier problem, and we can learn from quantum key distribution. Okay, and so basically, the concept that is important here is the concept of common randomness, which basically, in simple terms, is that Alice and Bob, have access to correlated random variables. So they have streams of data that are, or signals that are correlated, and they know the distribution that governs those sequences, and they can use this common randomness to be able to extract or generate a secret key. And that's basically the principle also of quantum cryptography. So basically, you can model this by saying Alice sends a Gaussian-shaped signal over a Gaussian channel, and it's quantized to yield some binary sequence. And now Eve has more noise than Bob. That's the assumption in this example. But then I will show you how to do that using the properties of wireless channels as we discussed in the last lecture. But basically here we assume that Eve has a worse channel, which means she has more errors than Bob. So in the second step, what Alice is going to do is it's going to, generate parity bits and send a syndrome, over to Bob. And so Bob is able to use those extra parity bits to just correct the errors, and so they arrive at the same. But Eve is not able to do that, and so Eve has more errors than Bob. Okay, and then we do another step, which is privacy amplification, which basically means that now I'm going to use a type of hash function to go from a larger sequence to a smaller sequence, where since Bob and Eve were able to, Bob and Alice were able to reconcile the bits, they end up with the same hash, but Eve is not able to do that because she has errors, and so she ends up with something completely different. And that's going to be my secret. Okay? And so this is not very different from what people do in quantum key distributions. They send these little photons, they measure the state of that photon, and then eventually they end up with Gaussian variables that are correlated, and they quantize that, and basically they analyze the number of errors, and based on the probability of error, they're able to estimate whether there was an active attack or not. And that's the beauty of quantum cryptography, and which we don't have in wireless channels, which is if Eve measures, this can be detected over the quantum channel. And so they do that, and they then basically, and this is the amount of information that Alice, Bob, and Eve basically have in each one of the steps. When Alice then sends error control information or parity bits to be able to reconcile, and so basically she's just sending, the amount of bits that is required for Bob to be able to recover X out of the signal Y that he received. Then this information also gets to Eve, and so Eve is able to correct some of the errors, and this is why you lose a little bit of your information here, but now they have exactly the same thing, and Eve also has a little bit more. But then fortunately, with privacy amplification, okay, you are actually able, through a hash function, to where you obviously reduce the size of your sequence, but now Eve has absolutely nothing because she ends up somewhere completely different in the space of the hash values. Okay? And so then the question when you, yes?
I didn't get what you mean by the common randomness in the previous.
X and Y are the, so the common residue is a measure of how close, X and Y are going to be, or how much, so how many bits can you extract from X and Y when they are correlated variables?
The same as, for example, a degraded loss assumption on the channel.
So basically you look at, there are several definitions for this, but one is that you create a new random variable that is a function of X and Y, and then you measure the entropy of that random variable, which is the function of those. That's one way, but then you can also use mutual information and other things. But basically, or conditional entropy, but basically it's this notion that you have a joint probability distribution of X and Y, and Eve has X and Bob have Y, okay? And now you're extracting information, or extracting bits that both of them can recover. And so you pay a penalty for all of this because you're sending reconciliation information. You have some security parameter here just to be on the safe side. And so eventually, when you started, with the entropy of X as the number of bits that you had, you're actually losing information. And so here, from a theoretical point of view, what you want to characterize is the maximum size of the key that you are able to generate with a system like this. Now remember that last time we saw that the channel is varying, and so you actually have times where the signal-to-noise ratio of Bob may be higher than Eve, even if on average Eve's signal-to-noise ratio is higher than that of Bob. And so how do you use that? You can basically exploit that by saying, okay, I'm going to build a protocol now that exploits these different phases. And even though very often I don't know exactly where I am, I can say, okay, I will assume that if Bob's signal-to-noise ratio is like 20 dB or 30 dB, and I know, and I will assume that Eve's is going to be at a different level. And then by making these assumptions, which is basically the same in practical terms as saying we're inside of this room and Eve is outside, by making this type of assumptions, you're obviously leaking information, but you can quantify it if you know the outage probability of the channel. And so then you can say, remember, best effort security, then you can say, okay, I'm going to use, when I have a positive secrecy capacity, I am going to share the common randomness, okay? Because that's when I have Eve getting more noise and more errors than Bob. And then here, this public part, I can actually send, all that reconciliation information, like the parity bits and so on. I typically can send that over a public channel. And Maurer actually in a beautiful paper showed that actually one way to communicate securely over the broadcast channel with secret messages is by having a public channel that everybody can see, where you are able to share information, and in that case you can actually communicate securely even when Eve has a better channel than Bob, or has less noise than Bob, by having a public feedback channel. And so this is exactly the idea that is used in quantum cryptography, and that we use here as well. And then once you have generated those secret bits, you can use those secret bits as a one-time pad, which of course makes your rate really, really slow if you want, because you have to generate one secret bit for every information bit that you send. Okay. Alternatively, you can use those secret bits as the seed for cipher. Okay. And this, what is the advantage? The advantage is that you can refresh your keys many times per minute, and so this means that the attacker would have to be, constantly discovering your key several times per minute, which is hard to do. So the protocol which we patented basically can be defined in this way. So you start with these random signals, x and y. You do the quantization. You generate parities, and so you check, whether your secrecy capacity is above a certain threshold, and depending on which stage you are, you either share common randomness, or you send reconciliation information, or you do privacy amplification. Okay, and at the end you have a certain key, and you do that on Alice and Bob, and then Mathieu Bloch came up with really nice LDPC constructions to do that. This is very deeply related with distributed source coding and with slap-in wolf codes and so on. The basic principles are very similar. Okay. All right. So how do we go to a system? So how do we build a system? So here's an example of a system we built for a Senza network that actually uses some coding, in particular also network coding ideas. And so imagine again this Internet of Moving Things, where you have all these devices spread everywhere, or Internet of Things. At the time when we were working on this, there was still this idea of smart dust, where I just have all these sensors that I throw everywhere, and they self-organize and do all that. So security broadcasting for that, or security bootstrapping for that, making sure that the system is secure, is really hard, because with all these little sensors and with very small power, so how do you actually ensure that they share a key and do that? So Virgil Gligor, previously in Maryland, now at Carnegie Mellon, he came up with this idea of key pre-distribution, where basically you take a pool of keys, you take subsets of those keys, and each sensor has a subset of that key, and with some probability, two neighboring sensors will share at least one key in common and are able to establish a secure link. And then they did all these maths with random graphs and so on to figure out how many keys, how big does the pool have to be, each of the sensors, how many keys should they have stored, and if you attack one sensor and you're able to get that pool, how easy is it to revoke that key pool and just basically ensure that the system is still secure. So this generated thousands of papers on how to do key pre-distribution. We thought a little bit different, which was to say, okay, when I set up the network, what if I have a mobile node that is used for bootstrapping? Okay, so what kind of protocol can I come up with that allows a mobile node to just go around, right? I can fly a helicopter, I can drive, I can, just ensure that there's a node that whose only purpose is to establish secure connections between these different nodes. Okay, so how do you do that? Well, suppose that I have node A, node B, and this is my initial node. And so, devices are very polite. So all the protocols start by saying hello, hello, here, okay? And now the security bootstrapping starts. So This guy says, I have key. Oh, the message has disappeared. Ah, let me see if I can make this. So that's the problem with cutting and pasting. So if I do this, aha, voila, I love PowerPoint. Okay, so they're back. So suppose that, one node, I put just one key. I don't put a bunch of them like in key per distribution, so I just store one key in this guy, and I store another key in this guy, okay? And now the mobile node is going to have a database that basically where he doesn't know the actual keys, but he has an encrypted version of those keys, and basically we use R. It's not a one-time pad because we're using it multiple times, but basically he has the XOR of any of these keys in R. Okay. So now he says, as I said, very politely, hello. And now this guy says, I have key number 327, and this guy has, I have key number 1422. Okay, so there's no problem in sharing the identifiers because I still don't know what the key is. But now, what does this guy do? Does anyone have an idea? You already had your network coding lecture, so you have to. So he does the XOR of those two. So what happens is that when the first key plus R, and you XOR that with the second key plus R, what happens? Right, the second key, the R disappears. And so now we know I'm able to send the XOR to this guy, the XOR to this guy, and now suddenly, each of them is able to recover the key. Right? So how many secret keys do I have? How many secret keys do I have? No, I don't have two because I leaked here, right? So then I'm only able to extract one. But the good thing is that I have, the attacker listens to this, so he has to guess one key to get the other one. So if he knows one, then he knows both. So I only have a secret of one key, but that's enough for me to establish a secure link, so now they can happily communicate with each other just using encryption. Okay? So very simple scheme, but then you can put this on steroids and do all sorts of things in higher field and for larger networks and how to do it and disseminate. That's the basic idea. And we actually implemented this in real nodes for an application that was basically to detect fire inside of a building. And so it's actually running in a real system. It's bootstrapped like that. Okay, so let me jump. So this was the old slide. Jump. Okay. Oh, I went back. I did. Yeah. All right. So active attacks. You asked about what if Eve can send stuff. Okay. When Eve can send stuff, it's called an active attack or jamming. Okay. And João Vilela and I actually looked at friendly jammers. So what if we have bad jammers and bad attackers, but we also have good attackers? So what can we do? And so, the transmitter wants to send the packet securely, and he has a couple of friends who are jammers. And so he's going to say, okay, can you please cover my back? This is just like soccer, One is going to try to take the ball as close to the goal as possible, and all the other players are there to make life difficult for the other team who want to get to the ball as well. And so the protocol can work, just using the request to send, the clear to send messages that you have. So in the request to send, you just send a list of jammers, and then they prepare their own jamming packets, and now you just say clear to send, and then boom, they just jam a certain area where they believe the attacker is. Okay, and so this assumes that you have an idea of the location where your jammer is, and so it combines also positioning and location. Okay. So we also implemented this at the MEC layer. None of this gives you perfect security, but it increases your security level at the physical layer under certain assumptions on your system. And so the other thing is secure network coding. Did anyone talk about secure network coding? And did you talk about network coding security, or will it maybe tomorrow? So let me tell you my view, just very briefly, of network coding security is that if I ask you, suppose I have a system where I can send 4 packets or 4 symbols across here, and I have 8 packets, so I send A, B, C, D this way, and E, F, G, H, okay? Or instead, I generate 8 linear combinations, and I send 4 here and 4 here. Which of these systems would you say is more secure? Left or right? So from an information theoretical point of view, they're both the same. So the eavesdropper has to guess 4 symbols here and also gets 4 symbols here. But from a practical engineering point of view, this is not the same. Which is, here you have, you know, this guy knows 4 symbols. This guy knows another 4 symbols. Okay. Whereas this guy has to solve, you know, a linear system without having all the equations he needs for that. So it only has 4 linear combinations and not 8, and likewise. Okay. And so even though they have to guess the same thing to get to the total information, this system leaks less information than this at these nodes. And the model for attacker is nice but curious, which is they follow the protocol, but they try to extract as much information as they can, which is very typical on the internet. Okay, so with Miro and Medard and with Zalima, we were working on how to formalize that. So what kind of security? And again, heresy. You cannot show that to a cryptographer because cryptographers think of security as 0 or 1. Either you have complete security, even though a quantum computer can break your ciphers, but either you have that total or you don't. But in practical terms and with very simple devices, you settle for the security definitions that you can get. And so if I can design a system that does this instead of this, then I should probably do that. And so that's one example of how to think about physical layer security and think about security in general in a different way. So there's more stuff in the book. The book is outside as well. And let me tell you, just it's one of the toughest things actually to write the book, and it was only possible with Mathieu. So Mathieu was on his postdoc, so he kept me on my toes. But it's very rewarding because in the end, you know, you have something that it basically compiles what you know about a certain topic at a certain point in time. It's very difficult because you have to be very disciplined, and you have to do another thing, which is you have to get comfortable into writing about stuff that other people did. And so when you write your own papers, you're mostly writing about stuff that you did, but when you have to write in a fair, rigorous manner about what other people did, that's really a huge challenge. So we tried to cite everyone at the time, and by now, of course, it's we need to do a second edition. We'll see. I'm sure it's not going to happen to me anytime soon. But Mathieu, either he's already tenured or he should be close to tenure. So maybe he'll take on the second edition of the book. Okay. So prototypes. In different parts of the world, people have been building physical layer secure systems. The pioneers were EMI Lab in Japan and WinLab in New Jersey at Rutgers. Nick Laneman with software radios started doing something. So Mathieu was a postdoc there, so they started building systems. And Steve McLaughlin, Georgia Tech, and we did some work as well on actually implementing it, although we did it at higher, using physical layer security ideas, but most of our work was on the protocols above the physical layer. So they were actually coming up with signals, measuring the correlation between wireless signals, and measuring secret key generation based on those signals. So there's still, I find, very little experimental work actually at physical layer security, and I would love to see more of that. Okay, so I have a repeat slide here, so let me jump. And so finally, yeah, how do you go from all of this to a business? And just a few comments about that. Security is really hard to sell because customers and people only see the value of security when something terrible happens. Okay? And so then you can measure and say, okay, so what is the cost when 1 million credit card numbers got leaked, like with Sony or this, and then it's in the millions and millions and millions. This doesn't mean that companies don't invest in security. They do, but it's still a very, very hard sell. And so security companies are really difficult to build. And I haven't done one, so I don't really know. But from talking with people, I think that for physical layer security, we still have a long way to go until we have something where you would be able to generate the right amount of capital to be able to bring it. So and this has to do with, again, with the number of people that we have working here and with how few people are actually working here. But I'm an engineer, which in the sense that if people are happy with cryptography and public cryptography, if that's doing the trick for people and there's no market need to do better than that, then maybe that's what we should be doing. But on the other hand, what I'm seeing as we design our own systems, where we're not basically selling security, we're selling vehicular networks or large networks, but where security is a feature that we need to have, many of the decisions are right now really being inspired by things like this, because we always have to have the trade-off between complexity and security. But again, you only know when then people go and hack and they attack your system, and then you figure out whether, and then you discover whether the system really is secure or not. Okay, to conclude. So when you look at classical cryptography under the computational model, so you should be, very, very objective and factual and reality-driven as an engineer regarding advantages and the disadvantages. And so clearly, the advantages is, so far, nobody has come up really with attacks that completely destroy, public key cryptography. So, and billions of transactions every day are based on public key cryptography, and so I'm the last one to criticize that. We should know that there's a risk that one day we may have a major catastrophe. And by the way, all the incredible hype now around Bitcoin, so Bitcoin has exactly the same problems as public key cryptography. So if we because there are lots of venture capitalists mostly, but also general people and entrepreneurs basically right now selling this notion that actually all our transactions can be done in a distributed way, and we basically bypass the banking system using a distributed currency that resides somewhere, and basically using ideas that cryptographers have actually known for decades, but basically to build a currency system that is completely independent of banks and governments. So there's a lot of excitement. I think there's a lot of research to be done there, but the assumptions are the same, not being able to factor large integers and so on and so forth, just like public key cryptography. So there's a problem there. Then the processing is fairly easy. You can do it block by block, various ways. If the cryptographic primitive is secure, so if you believe this premise that there does not exist a quantum computer that can break it, then actually everything is secure, and you don't have the type of coding dependencies that you have. And on the other hand, and this is the economic business argument, is that systems have been available for a long time. They've been under attack for a very long time. The technology is readily available, and it's cheap, right? So there you go. And so what is the disadvantages is that there is a risk. People are running a risk, and there's many people are oblivious to this risk, so they don't realize it. It's very hard to measure how strong actually a cipher is, and there's no connection, so people just separate the communications piece from the encryption piece, whereas in information forensic security, we can actually quantify this, okay? And so basically the way that you measure a cryptographic protocol is by making it public, letting as many people attack it as possible, and then if it survives all these different attacks, differential attacks, linear attacks, blah, 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 then essentially you say that the protocol is secure. So it's secure until someone is able to find a smart way to break it. And then basically, if you look from an information theoretic point of view, actually, the secrecy capacity of these systems is 0, because you always assume that you have a clean channel between Alice, Bob, and Eve. And so from a theoretical point of view, this is basically completely unproven. So what I find is that sometimes it's a little bit unfair from cryptographers or from people in classical cryptography is that they put such a huge burden of proof on information theoretic security when their assumptions are, really, bogus from a theoretical point of view. Now, what are the advantages is that, of course, you have no complexity restrictions on the eavesdropper in terms of computational resources. So the eavesdropper can have all the computers and quantum computers in the world. You can actually, and this is what I like as an engineer, you can actually be quite precise about how much you are leaking. And so this probabilistic approach to security is actually quite common in the network security community. So you have the cryptographers, mathematicians who think this is heresy, but then you have a whole community that is designing secure protocols where it's perfectly normal to say, for example, in a network where I have intruders, I am able to detect an intruder with a certain probability. And then if the intruder does this and this, and you have a probabilistic model of the intruder, then you are able to react that, based on some stochastics. And so with network security people, and maybe that's why I feel more comfortable with this notion of probabilistic security, is able you just quantify things, and at the end of the day, all of this is about risk management. And so when you then talk with risk managers, what they do is they quantify the likelihood of certain events, and then they design solutions or processes or whatever that provide you, with contingency plans and so on for a certain that are activated with a certain probability. And so conceptually, there's not such a big difference from an engineering perspective into looking at security the same way you would look at risk management and just use probability theory. So quantum key distribution is actually implemented and used, I wouldn't say widely, but basically in the banking sector, you do have quantum key distribution schemes. Wireless solutions are starting to appear, as I mentioned, and hopefully we'll soon have actually codes that are not that long, but are still very close to perfect secrecy. So the advantages is that you are always averaging in information theory in general, and so you end up always with some kind of probabilistic argument behind that. So it requires assumptions about the communication channel, and this is the biggest limitation, is whether I know the channel or not, under what conditions. And so you want a solution that works for 99% of the cases. And so this is the biggest limitation right now. And then basically, these systems are still very expensive because they're not massively done and they haven't been optimized. And basically, there aren't any products beyond that application that I showed you, to the best of my knowledge. And so at the end of the day, from an engineering perspective, there's still a lot of work to do to clarify many of these issues. So one last piece of advice, which was given to me actually by Bob Calderbank, which I really love, and I'll just share it with you, which is how can you place yourselves as researchers, as scientists in the overall scope of thing, and how can you define a strategy? And I think it's really important that you start thinking early about strategy and impact. And at the end of the day, you want to be doing something meaningful that actually, brings something positive to as many people as you can. I think that is a worthy goal. And so Bob Calderbank, when he was head of AT&T research, basically he evaluated people as rectangles, okay, where one side is technical depth, okay, and the other side is practical relevance of whatever. And there's always this discussion, which I find very boring and useless, about theory versus practice, and elegance versus messiness, whatever. But basically, I think that it's perfectly fine if you want to be a theoretician and be really, really strong and deep. So this means that if you want to do theory work and you don't want to care about the practical relevance, to maximize your impact, at the end of the day, what matters is the area of your rectangle. So if you want to have to be a theoretician, and you want to have impact, and the impact is measured by the area of this rectangle according to Calder-Brack's model, okay, then you're a skinny rectangle, but who has to be really, 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 really deep, okay, and you don't care about the practical relevance. But this is really, really hard. So it's very hard. You have to study a lot and do a lot of math and be, very, very, very good to be able to have a very strong impact in theory when you're at this level of technical depth. Okay. Then, if you want to be a systems person, you want to build, things that work. Then, of course, maybe you don't need all that technical depth from a mathematical point of view. But then you're skinny in this direction, but then your practical relevance has to be very, very high. So your systems have to work, that's the number one. And they have to work in the real world, not in Mars and Jupiter. Some of them have to work in Mars. But anyways, you have to be really skinny. So to get to a large area, you have to be able to do this. And now the question is, to maximize impact, what's the easiest way? And I have found that the easiest way, at least for me, is to be an experimental theorist, which is basically, you might not, you aren't able to go as deep on mathematicals and other things because you are looking at all these other things that are necessary to be practical relevance, and that also takes a lot of time. And again, it's not, and I really hope you trust me on this one, which is it's not, the amount of gray cells and intellectual ability is the same in all these aspects. It's just different ways of thinking, and we have to be very careful at not being, mathematical snobs or theoretical snobs, because we have to realize that understanding this, what is practical relevance, how to design a strategy, how to make something that is relevant, requires as much brain power as solving really hard mathematical problems. Okay? And it requires another thing, which is communication skills, which is really, really hard. Okay? So this way you can maximize your area. So when you think of where to go and what to do, think a little bit about this. So final thoughts. Security is an interdisciplinary field. So go talk with cryptographers, psychologists, economists. Again, the really big problems in the world can only be solved when you put lots of heads that know lots of different things together. And this is very difficult. It requires, again, curiosity, open-mindedness, tolerance, and it requires communication skills. And so all of those things that I think we need to train young people to do much better than we do at the university right now. So I think we focus too much on tools. We don't focus enough on actually finding the right problems and finding the good problem, important problems. Okay? So we need a lot more people working on information theoretically inspired protocols, I think, systems and prototypes. So that was the slide with the little people that I showed you. I think this, if I was a student today, I would try to learn as much about networking as possible and try to use information theoretic theory in general to just think about how to design better systems. And so my timer is telling me that I should probably stop. And so systems and prototypes, then we need to understand better how to close this gap to have impact in the real world. I have tons of ideas on how to do that. Some of them I was able to try out when I was director of the Carnegie Mellon Portugal program, which was a large government initiative followed by the Portuguese government, where one of the things we tried was to have researchers spend a few months in the industry and have industry people spend a few months in the universities so that they finally are able to understand where each are coming from. And so as grad students, don't stay in the lab during the summers. Tell your advisors you want to go for 2-3 months to a company and go get out of your comfort zone. And then you are 2-3 months later with your PhD thesis. Who cares? But at least you will know. I mean, I worked for a few months, not very long, at Siemens in Munich. And it was enough for me to know that I never want to work in a major corporation ever in my life. But I understood better how people there think and what are their worries and why certain things take more time and so on. And so finally, I think regarding this whole field, I think we just started to understand the problem, and there are lots and lots of opportunities, but I think you have to go outside of the lab to find a lot of that. So let me conclude with acknowledgments to a bunch of amazing people that I had the good fortune to work with in this field and others. and this is our research group somewhere in Porto. All right, thank you very much.